Well, scrambled all those. No, that's kind of Martin.
I'm here at least 3 days a week.
The error keys and they do work.
Okay.
Yeah.
No problem. No, my grandfather recently taken my job was a paper shop. Get me talking in the right. Probably what I want to be doing when I started doing research.
Okay, let's get started. Let me have your attention, please. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker, who is Dr. Thomas Zacharia. He's the Associate Laboratory Director for Computing and Computational Sciences at the Oak Ridge National Laboratory. Tom received a PhD from Clarkson University in upstate New York in 1987. His PhD is in Materials Science and Engineering, so he is an engineer. He joined Oak Ridge National Laboratory as a postdoctoral appointment in 1987, and he rose through the ranks. From his postdoctoral appointment, he became a research staff member, permanent employee, and then he became a group leader, and then a division director, and then in 2001, he became an associate laboratory director, which is a position he holds today. The title of his presentation is Leadership Class Computing, an Instrument of Innovation. Ladies and gentlemen, please welcome Dr. Thomas Zacharia.
Good afternoon. Thank you very much. Thank you for having me. I realize that particularly for those of you students here in the program, Lee has arranged for you to sort of get the extremes, bound the problem as to where you want to be in your career. To start with Weinberg on one end and Zacharia on the other. It's a pretty broad spectrum, and you should be able to find your niche in life somewhere in that broad spectrum. As Lee mentioned, I started as an engineer. Actually, my undergraduate degree is in mechanical engineering, and came to work at Oak Ridge, believe it or not, in the welding group. And when I went through my PhD program, I never thought that I would end up being in the welding program at Oak Ridge. I thought I would finish I finished my master's, went back to India, got married. I thought that was the end of it, go back and work in India. Then I thought, PhD sounds like a good idea, go to the U.S., spend three years with my new bride, get to know each other, and then we will go back. And my first paper out of my PhD was presented at the Gatlinburg conference that Oak Ridge organized. And it turned out, this was little events in life that take you to unexpected places. So Stan David had actually justified a postdoctoral position in his group and offered the position to somebody who then subsequently got a job. And so he ditched the postdoc And you know how it is in the DOE world, you have milestones, and so a postdoc was required. And I think in that year, we were the only two people who were interested in material science modeling and simulation. So after my presentation, Stan came to me and said, hey, would you like a postdoc position? And I said, oh, I think I have another year to finish my PhD. And my advisor said, oh, if you're good enough for Oak Ridge, you're good enough for me. Write it up and go to Oak Ridge. So that's how I ended up at Oak Ridge. I have a tendency of getting bored with status quo and keep pushing and asking why not. And so pretty soon I ended up being in computing, and it turned out that I'm leading the computing program at Oak Ridge. And about a couple of 3 years ago, we felt at Oak Ridge, we felt passionately that perhaps the time has come to view computing as a new scientific instrument. And I use it to distinguish computing from what generally, there's a lot of database work, a lot of computing that is done at all scales. And in some sense, computing in computational sciences suffers from its successes and how pervasive computing is. And so at the end of the day, the people who fund computing looks at it and says, well, people who do computing on a $799 Dell PC if it's a laptop, and $599 if it's a desk side. I know, I just bought one for my daughter, who's a UT student, by the way, in engineering. And so how do you, and then suddenly talk about $10 million computers and $100 million computers, and one commonality between all these things is that even the $100 million computer becomes obsolete in 3 years. And that's a very difficult pill to swallow for many, many people, unless you think about it as truly a unique scientific instrument capable of producing fundamental new discoveries that could otherwise not be possible. And secondly, if you don't, if you get this idea that, well, you invest $100 million in something that's sort of like a perishable good, like, apples, pears, fish, what have you, put it on the counter. You buy it, and you have a finite shelf life, and you got to take it out. And so you had to convince people who provide the funding that, don't think about it as buying a computer. Think of it as a new scientific facility, and think of it as just an operating budget for sustaining this capability. So it is not really about leadership class computing. It is really leadership class computing facility, a new scientific instrument. At least that's the story, and we're sticking with it. So let me tell you. So if you think about instruments of innovation, the general faculty of human being have not dramatically improved over the last, decades or centuries. But really, at any given point in time, if you look at the new science or advancement of knowledge, can always tie to some new unique instrument, whether it is the spallation neutron source or the light sources or the microscopes or what have you. And so we believe that leadership class computing, as we envision as Office of Science, and now Congress and appropriators are supporting it, would truly lead to some new scientific discovery. And if it is not, 3-4 years from now, I'll stand before you and say, boy, that was a dumb thing to do. Even I hope I will not be. So since I knew that Weinberg had talked to you last week, what makes a laboratory unique? About 30 or so years ago, Alvin Weinberg said, a laboratory, a multidisciplinary laboratory, is a powerful instrument of technical, scientific, and social progress. A unique combination of mission orientation and discipline orientation. That is, laboratory is a place, unlike university, where on the one hand you are able to do technical stuff because curiosity-driven research, but it still has to be within some overall context. And a flair for getting after very big and difficult matters, because it's truly an area, a facility where, or an environment where you can have large interdisciplinary groups tackling some substantial problems of interest to the nation and indeed the well-being of humanity. And in the time that it took from Weinberg to go from kind of this picture to the one below, I thought we should look at what big means, because if you really think about it, big projects are getting smaller. We still think in terms of, $10 million projects is big, or $100 million a big project. If you just simply do escalation, what you find out is that in the time that it took for him to morph, you see that, like a $20 million project 30 years ago or so, or 35 years ago or so, is now a $136 million project. Just to put things in perspective. And so, in some sense, I believe that at the laboratory, when we are investing so much, and truly at Oak Ridge today is really a unique place because of the investments that are being made, not only in computing, but phosphorylation, neutron source, the Center for Nanophase Materials Sciences, biological investments, in material science, and in a variety of areas. Dave Hill is doing a wonderful job of revitalizing the nuclear science and technology portfolio, fusion energy. We have an obligation to think big and deliver on it. And even when we think big, and I believe that a $100 million a year project is huge. If you look back to the Weinberg era, it was a big project, but it's at a $20 million type of a project. So we are not really out of the realm of possibility. The really big questions, if you look at it, there have been a number of workshops that has led up to this leadership class computing in crafting the national program that both White House and Congress and Office of Sciences really come together on. I mean, clearly, the life sciences, there's tremendous opportunities. Very clear that we've only scratched the surface in terms of bioinformatics and sequencing and what we do with the information, sequence information. Proteomics is coming just behind the corner. Let me just give you a sense of scale. The Center for Computational Sciences at Oak Ridge National Laboratory was established in 1992. 12 years later, the cumulative data that we have in our archival storage is of the order of about 300 terabytes. Okay, that's a lot of storage. The Genome Live facility that the DOE is planning in the biological sciences area, when they come online in 2008, if they come online in 2008, the projected data rate is 1 petabyte, which is 3 times the cumulative storage of the last 12 years at the laboratory. 1 petabyte per day. We don't know how to deal with these kinds of data volumes. These are pretty amazing challenges that truly will be pervasive and something that the national laboratory and the university partnership should be able to tackle in an effective manner. Clearly, astrophysics, how we came to be, these are fundamental questions. And Tony Mazzacapa at Oak Ridge and he's got a large group of about 200 people spread across the U.S. tackling some of these problems. Of course, there are some people thinking in terms of the impact of technology and humanity and vice versa. For example, yesterday we had a LDRD review where somebody was looking at the impact of nanotechnology, trying to understand intended and unintended consequences of new technology that's being deployed. And I mean, basically, answering these big questions requires boldness to engage opportunities, new approaches and infrastructure, new collaborations and interdisciplinary partnerships. And if you really look at it, there is an underlying theme to all these things, which is complexity. How do you deal with complexity, different temporal scales and as well as spatial scales? I just want to leave you with a couple of quotes here. One is from Jack Marburger, who's a science advisor to the president, and of course Ray Orbach was the Office of Science Director. But basically, both OMB, Office of Management Budget, and the Office of Science and Technology Policy is saying is that, look, there's a new frontier in science that we're going to tap into based on the unique instruments that are being deployed, both experimental and computational. And of course, we would like for that statement to be backed by new money. In some instances, what they say is that you need to reprioritize and refocus. But the reality is that this is where the investments are going to be. The science of the 21st century, simulation and high-end computing are equal partners with experiments. And of course, this is something that we can have a wonderful debate over as to what's the role of simulation and experiment. But the reality is that there are many areas. I believe in nanotechnology is one, or biotechnology is one, where computing will lead to new discoveries. For example, when SNS comes online in 2006, maybe 2007, for the first time we'll be able to measure volumes in the 5 nanometer scale in soft materials and biological materials. And around that time frame, we will be fielding a 250 to 300 teraflop machine. And at least in some areas, we will be able to calculate from first principles phenomena at that spatial scale. For the first time, we'll be able to overlap what we calculate using, first principles calculations and experimental measurements. And we hope that it'll lead to some really new insights into this new science. Again, this is not going to happen simply because we build big machines. Building big machines, building big computers in of itself doesn't do you anything unless we make the investments to have new developments in mathematics. If you go back to 30 years, 40 years during the householder era at Oak Ridge. Oak Ridge was a premier place in the world for mathematics. We are not today. We have some very bright people, no question about it, but we are not the preeminent place in mathematics in the U.S. or for that matter in the Southeast. But I will tell you that we are in the process of rebuilding that, and I believe that we will succeed. And it's not going to happen by ourselves. It's going to happen in partnership with the University of Tennessee. Same is the case in computing, in computer science. Again, we have an excellent opportunity for building and bringing together people to this enterprise. Because of this, some of the activities in computing, we anticipated hiring about 45 new people into the computing directorate this coming year. And we've been hiring about 30 to 40 people every year for the last 3 years. So this is a growing enterprise. It's an opportunity to attract new people to this area. So with that as a backdrop, basically what happened was that Congress appropriated funding for starting a leadership class computing. There was a competition that was held in April. We were given 6 weeks to write a proposal, basically a 20-page proposal, $400 million, $50,000 a word. So you choose your words very carefully. And there were 4 proposals. It was open to only Office of Science laboratories. There were 4 proposals that were submitted. After the proposal was submitted, then we had a oral presentation to a review panel selected by Office of Science, and so we went through a whole day of review, and subsequently the Oak Ridge proposal was chosen. And basically the focus of the proposal was to develop capability computing. So the idea is that the whole point is not to build a big computer so that you can serve large number of users, which is important. But the idea is to see that if you actually justify building a big machine based on a unique scientific problem that you're going to solve, then what are you going to do to make that a reality? And so we actually said that, okay, this may be the first time we can transition the use of high-end computing towards a major scientific use of facility. And so we adopted the concept of end station that many scientific facilities, whether it's light sources or spallation source, has. So it's basically teams of people coming together along with unique experiments in the case of SNS, experimental techniques, and in the case of this leadership class computing facility, unique computational science tools, which will then be used for supporting new science. And it'll be peer-reviewed and it'll be available to anybody in the country. So it's not just an Oak Ridge. It's not just for Oak Ridge people, nor is it just for DOE. It's really open to NSF as well as industry. Our vision was to offer a new capability for science for the nation, be a focal point for scientific research community as it embraces computing as a peer in terms of experiment and theory, provide the leadership and organizational framework. So the idea is just like with the major facilities that we will actually support driving the science and, of course, focus on a critical set of national problems. These are the problems that DOE has identified as strategic. It's directly from their strategic plan as to where they will be investing a lot of efforts in nanoscale science. It's not just DOE, it's a national imperative. Tremendous amount of resources are being spent by NSF, DOE, and basically in the physical sciences, and everybody agrees that computing is going to play a major role in, along with the experimental techniques to drive some of the developments. Similarly, in biology, computing is expected to play an important role. Climate change modeling or fully coupled Earth systems models, it's something that clearly computing is going to lead the way. Fusion for energy. The times where we are going to build prototypes after prototypes is probably behind this. In fact, there was a workshop that was held a few months ago looking at radiation effects in materials for the EDA program. So the idea is that we would at least be able to down select and understand the impact of material behavior in this kind of an environment, so that again you can minimize the number of expensive experiments, and again astrophysics type of work. Well, there we go. Our plan, just to give you a sense, is that, so we, as I said, we proposed a $400 million for 5 years was a proposal. The plan is to field a 100 teraflop machine in 2006, 250 teraflop machine in 2007. We already have laying the groundwork for the network that needs to be connected to this facility. If you think about it, and again, this is being done in partnership with the University of Tennessee. Your typical campus network today is probably a gig would be my best guess. We are actually talking about laying a network fabric both within Tennessee as well as connecting to the national network and also to the international network, at least by an order of magnitude, perhaps 2 orders of magnitude more bandwidth. So the idea is that this machine, even if it is in Oak Ridge, should be available to folks here and elsewhere as if it is physically located for most applications, so that you can actually move data back and forth very easily. Again, the focus is not just to build a machine and throw anybody and everybody onto the machine, but really to work with the applications to code, to develop the software specifically targeted for this, and to select the applications appropriately. Again, work with the communities and look for continued. Every 3 years you got to throw this machine out and bring a new one in. And after 3 years in my current job, I must tell you, both my boss and my colleagues have significant sympathies for me because, Tom Mason, I know, he's got a heavy lift. But once he gets that concrete on the ground, for 40 years he's set. He doesn't have to go about worrying about when to bring in the next SNS. For us, as soon as we bring the machine in, we are planning the next acquisition. And usually you're buying the first one of its kind. It's both interesting, intriguing, but it's also a lot of challenge. I'm going to skip the slide, but basically to say our strategy is to build on Oak Ridge's strength and our university partners. This is something that I really want to talk to you about, and that is this is sort of the proposal, the roadmap. Some faces you will recognize, say our UT folks. The proposal had about 60 letters of support from some of the top, universities and institutions. There's really a national partnership. I think it's important because, again, for us to be successful, for this enterprise to be successful, it is not enough that we just build a machine. We have to do the right kind of science, and we have to have the broad scientific community engaged in delivering this. And we believe that this is just a snapshot of a few pictures that we could put together in the view graph, but we really have an extensive partnership. Oak Ridge has been engaged in many of the new computational science programs, which has been very, we've had a successful track record in competing for peer-reviewed proposals. World-class facilities that UT Battelle invested private sector funds in, and again, a sustained path to leadership computing. And I think that's very important when you ask a community to invest their time and effort. If I were to come to you guys and say, please focus on simulation of nuclear reactors of the future, and you spend 3 to 5 years of your life building the capability, and if we go away by the time you're ready to run, you're not going to be very happy with us. And so our commitment in our proposal was to say this is not something that is a one-time thing, that we want a sustainable path for the future, at least 12 years so that I can retire. Some of the key areas, we had, leading up to this proposal, we had a large number of workshops, and we will be having a lot more workshops as we look to the future. Basically, each of the community coming in and saying what kind of capability they need. So from 50 to about greater than 100 teraflops today to tackle the kind of problems that they know how to, and they are important and problems for the nation. This is not an exhaustive list, and by no means do I want to give you the impression that these are the only things that we'll focus on. In fact, it'll be much more extensive, and we'll continue to engage more and more groups. Let me give you a perspective on where we are. So what we proposed was a Cray system. Cray sort of invented supercomputing, Seymour Cray. It went away, bought by SGI, then sold back to a small company which renamed themselves into Cray, Inc. It truly was something that was, Oak Ridge was like salmon swimming upstream, because it would have been a lot more easier to say, we'll go with IBM. The old saying that, nobody has been ever fired for buying an IBM. They have very good machines, they run, there's not an issue. The problem is that they are, over time, the power series of machines, which have been very successful, have been driven increasingly by the commercial sector. So we tried our level best to run scientific computing on servers that are basically built for Google. It's just basically database engines, and so they have different needs, different balances. So if you look at where scientific computing is going, the computational requirements are increasing. People are looking at more and more complex problems to solve. At the same time, the relative memory and interconnect latencies are getting also larger. So the amount of time it takes to fetch or prefetch data from memory to the processor is getting larger and larger. So even though your CPU is able to compute very fast, the data that it can compute on is getting there slow. So you're getting, in the case of Power 4, for some of the applications, you're getting 1% of peak. So if you have a machine that is rated at 1 teraflop, you only get 1% throughput, which is not a good situation. Power consumption is increasing. At Oak Ridge, we have an acre of raised floor computer room to place these machines in. Heat generation is continuing to increase. You've got to cool. Not only do you generate the heat, you got to cool it also. The complexity and software complexity, both hardware and software, is increasing as well. At the same time, memory bandwidth, interconnect bandwidth, I/O speed, so the data coming out of the machine after you're computing, all those things are decreasing. So the idea of going with Cray was that we felt, in fact, we had several meetings with IBM asking them whether they would redesign their machine or at least design a machine for us. And I will tell you in this audience that the only I understand the only rationale that IBM would accept as part for redesigning a machine would be a national security imperative, because otherwise it is not part of their cost model, and that implies that these machines will cost much like the aircraft carriers, so it just becomes prohibitive. So what we proposed was a Cray X1, which is a scalable vector system. It's a single system image. The idea is that you should be able to have access to data no matter where the data is located. It's a complex machine compared to what we are generally used to. We are still learning how to best utilize it, and it is my sense is that we will learn with the X1 as we go to the larger X2 machine. The machine complexity will become lesser, and we would have had codes that are migrated to the vector machine. We also, just as a hedge, we also looked at, we proposed a Redstorm as another 20 teraflop machine that is scalar machines. So those things that run very well on scalar systems should run very effectively on this. For those people who follow the ASCII red machine, it's basically a commodity processor with a very, very fast interconnect technology. Also, we proposed a Blue Gene system. Now, which is an IBM built design machine where basically the advantage is they are using small processor and memory systems. So these are the three initial prototypes that's going to come in, and based on how they perform, we will either build a hybrid system that includes one or two of these or build one out to a big machine. Just to give you a sense of why we chose Cray X1, this is the same data presented in two different fashions. So this is an ocean program, ocean simulation model. It's a latency-sensitive application. So this gives you a sense of how the machine performs if the data, if the computation is latency-sensitive. And what you see is the green plot is the current fastest machine, the Earth simulator, which actually was designed and built to do climate simulation. And the X1, for a similar size machine, does 50% better than the Earth simulator, and then significantly faster than any other alternative that we have. And this particular one basically is normalized. Instead of comparing to processors, what you have done is the lower axis is processors times the rated flops of each of the processors, so that it is relative to peak performance. So what kind of performance can you get if you bought a machine at a 1 teraflop machine or a particular size machine? This is what you can expect. The same data presented as number of processors. The bottom line is that for latency-sensitive application, this machine far surpasses anything else that we have available today.
Yes. Is the Earth simulator, is that the Japanese machine?
It's a Japanese machine. They built a 40 teraflop machine. It's the fastest machine right now. They spent $300 million building. It still lasts 3 years. This is a bandwidth-sensitive application. It's a fusion application. And again, what you see is that the performance is factors of better than anything else that's available on the market. So this was really the basis in which we chose to go forward with a the proposal for the leadership machine. Can now do some what if scenario. This is just to sort of bracket what is possible. If you basically say, this is what we have right now at Oak Ridge, this is what we expect to get at Oak Ridge by end of this year, December time frame. You can look just based on the performance differential with other machines available today to get similar performance as the 6.4 teraflop excellent. You can basically see how big a machine that you have to buy of other vendors. And so again, this is just to give you a sense that this is truly a remarkable new capability for computing. It requires coding specifically for it, but it still gives you an opportunity to simulate something that has not been done before. And so I would strongly encourage you to find out a little bit more about it. Just wanted to say that if you haven't been to Oak Ridge, that's again something that I would encourage you to do so. The new facilities are wonderful, and it's certainly, we've tried hard to give a campus-like environment. And this summer, we had lots of students come to Oak Ridge, work with us, and we will continue to have a lot of students with us. We have a state-of-the-art visualization facility, which if you haven't seen, it's a great capability for analyzing the data. As I mentioned before, we connected to the rest of the world in a way that we've never been, and in so doing, we've solved the problem for the state of Tennessee. So as part of the partnership with the University of Tennessee, and also Vanderbilt, we're going to have a very high-speed connectivity going from Knoxville campus all the way to Memphis. And so again, to coalesce around some teams among the universities and laboratory here to compete for major programs nationally. This is basically, we have a program, this is roughly about $10 million a year to continue to look at next generation architecture. The idea is that we evaluate today for those machines that we will buy 3 to 4 years from now. The leadership class computer is roughly funded at about $60 to $70 million. This is a SIDAC program which is funded at about $60 million a year. Not all of that money comes to Oak Ridge, but a good fraction comes to Oak Ridge with the idea of delivering science. So in a short period of about 4 to 5 years, we've gone from about a $7 million program to now about a $100 million a year program. It's not enough that we just count the dollars. Now we have to really produce and deliver on it. In fact, the last on-site that we had, one of the things that Ray Orbach mentioned was that, it is a sobering time to come to Oak Ridge because so much has been given to Oak Ridge, and it's time for Oak Ridge to deliver on those promises. And we're not going to do it alone. We're going to do it in partnership with UT and other universities. Partnership is key, and again, this proposal had many university partners, really top-flight universities: Columbia, Brown, Georgia Tech, Vanderbilt, California, University of California, San Diego. The list goes on. And then, so it's not, to me, what is really exciting about this project is not the building of the project, but the collaborations with some of the best minds in the country and even internationally. Let me take a minute to talk about a small initiative, but something that can be very profound in my opinion. It has not been oversubscribed yet, and this is something called Computational Sciences Initiative. I don't know whether you've been briefed about this at all. So basically it is UT Chancellor sets aside $1 million here that was previously being spent to keep a very old IBM SP on campus. The money never leaves the campus. Money stays here on campus. What I committed to the university was that if you set aside that $1 million at the university for faculty release time, for enhanced graduate student stipend, postdoc support, what have you, that we will make resources, computing resources available at Oak Ridge to support the computing program. So the point really is that the intent was to use this as a seed money. For those people who are familiar with the seed money program at Oak Ridge, it's not a lot of money for an individual, but it's enough to form partnership between UT and Oak Ridge, perhaps support a graduate student, perhaps buy a summer time for a faculty, but really to take on a new problem that requires high-end computing. And there's resources available. The Science Alliance administers the program, and if you need more information, please contact me and or Jess Poor. But the resources are available, and I think that it's a great opportunity to continue to build between UT and ORNL. The Joint Institute for Computational Sciences is yet another new facility that the state of Tennessee invested in. Tom Dunning is the director. We are currently recruiting 6 joint faculty positions between the computing program at Oak Ridge and various departments here. Currently, we have an astrophysics position, chemistry, biology, computer science, math, and again, we're looking for opportunities to expand. Our goal is to have at least 36 joint faculty positions in computational science between UT and ORNL. And again, establish strong student programs. One of the things that we want to do is, let's take, for example, nuclear engineering as a case study. We want to have a summer institute where, if you want to tackle a particular grand challenge problem, the idea is to bring, say, for about 6 weeks, world leaders in nuclear engineering, mathematics, computer science, high-end computing, and bring them together, not necessarily to solve a problem, but really to define a problem, and then go back so that we can, collectively as a group, you can work through that. And again, that's something that we will support and sustain over that period of time. We also have strong outreach activity. This is a new workshop or conference, whatever you want to call it, that we started last year. The ASCII program, if you're familiar with the major computing initiative out of the weapons labs, they have a conference called the Salashan Conference. Basically, 60% is by invitation only. 60% of the invitees always are common, and they returning invitees, and 40% are new, just to bring new ideas. And it's not one where everybody comes and talks, but they have panels and discussions and really try to push the field forward. And we are trying to establish something like that. And again, I would, look for ways to engage UT broadly. So where do we go from here? Both for Oak Ridge nationally, but also as UT and ORNL in partnership. Clearly, it's easy for, there's only finite resources, finite time. You cannot do all things, and you cannot be all things to all people. But we have a unique opportunity to do something fundamentally different in computing and computational sciences. We have to prioritize, because if you have if you don't prioritize it, that means we really don't know what it is that we want to do, and also make the intellectual commitment to support and sustain that, whether it's technology or applications or a driving problem, choose a direction. And I think it's important to think at appropriate scales. It's very easy. I mean, I can tell you that when we were talking about $100 million a year computing 2 or 3 years ago, the politically expedient thing would have been to say $10 million, and we've had this discussion, $10 million would be easy. It'll be easy to sell it to Office of Science. It'll be easy to sell it to Congress. But it would not have been a substantial difference. We would not have done anything differently. I hope we will do something differently with this kind of investment, or else I would be the first one to say that we have dropped the ball. And again, taking bigger risks goes with the territory if you want to make a substantive change. So I think I'll just basically say that I mean we're just in the very very early stages of a very interesting and challenging project, and we're looking for ways to interact and collaborate. So with that, I'll take questions.
Okay, we now have time for questions and comments from the audience. Don't everybody speak at once. Bill?
Is there an online newsletter, information letter coming from the division or the directorate?
The answer is no, but it's a good question because it's something that has been recommended. We've been asked to have a new sort of newsletter that keeps abreast of what's going on. It also makes it easier for people to sort of get engaged slowly. So we're working to develop that, but no, not at the moment. The most recent issue of OR&L Review has a good summary of the computing program in the laboratory.
Other questions or comments? Yes.
You said the new machine has, you can't use the same programming models you already have. You can't use MPI and MP programming.
So, like everything else, it's an elevator speech. So the answer is you can use MPI, but it performs poorly. It is not. That programming model exists. It is not being optimized for this machine. Now there are some programming models that works very effectively. So the question that you have to do is whether the portability becomes an issue. So it's something that we have to work with the users to either improve the MPI performance on the machine or go to a different programming mode, Core, Fortran, or something that'll give you the kind of performance on the machine. And it's very early. I mean, to put things in perspective, we have 8 cabinets of Cray X1 at Oak Ridge at the moment. Each cabinet is $10 million, so that's $80 million. And that's only a 6.4 teraflop machine. What we are hoping to bring the next machine that all these developments will go into will be a 100 teraflop X2 or Black Widow or whatever the code name is. And that's going to be, so for a 100 teraflop machine, it's going to be only $100 million. So you had to engage Cray and that expensive front end to drive the technology to something that is affordable, but also now we are influencing them in terms of what are the programming models that is needed and what kind of libraries and software tools and so forth. So we're developing that as we speak.
I have a question. You had those 5 areas that you mentioned, the grand challenge areas. Which one of those areas historically has been the biggest users of
Well, it changes with time. Today, I can tell you that 40% of our facility is currently dedicated to climate. And the reason why it's dedicated to climate is that there is an intergovernmental panel on climate change. It's a policy group among the various governments that decides on free trade and NAFTA and emissions requirements and regulations and so forth. U.S. is getting ready to sit down with the rest of the world to negotiate that agreement. And so they needed the climate, the climate runs to assist the policy. So in fact, even though we've all dedicated 40% to that one singular problem for the last almost year, in fact, just last week, we had a request from DOE asking whether we could actually increase that because there is really some evidence that, in fact, it was there even in CNN yesterday, that, climate, the pollution and greenhouse gas emission is not a localized phenomenon. And so what emissions in China has an impact here, and so we really need to understand the global scale of the problem. But it'll change. I mean, I think that fusion is another application, or if nuclear comes back in a big way, which I think it will. These are, if you look at the main weapons codes, the Nike, the Dynam, all those things, the big finite element codes, those are all generated from the nuclear era. And I think, for example, we are already anticipating the needs for engineering simulation, and we have a robust effort to build the next generation codes to run on these machines. So who knows what it's going to be tomorrow.
Okay. All right. I think with that answer that we'll end today's colloquium, but I see several new faces in the audience. And so new faces may not be aware that we do have refreshments downstairs, and everyone is invited, and you'll have an opportunity to ask more questions to Dr. Zacharia. But before we adjourn, let's express our appreciation again to Tom for his presentation. Thanks.
I have a CD, and Debbie gets it.
I'm Mario Fontana. I worked at Lab for a long time. Started in welding.
Yeah.
Actually, Pete Patriarca and
I know who he is, but I never worked with him. But I did.
well, I think the mark.
Show him where it is in a second. He'll be there.
Watch with his metallurgy.
Yeah, and Khrushchev was.
Yeah, that's right.
How you doing? Good to see you. Go down. Let me get on there.
Weinberg-Wigner's theory of neutron chain reaction. In the preface, so we're concerned, a lot of students nowadays. So much dependence on